This video will be about how to do curve curve sketching. So first off, we need a few definitions. Increasing, a function f of x is increasing on an interval from a to b if a less than x1 less than x2 less than b implies that f of x1 is less than f of x2. Decreasing, a function f of x is decreasing on an interval from a to b if a less than x1 less than x2 less than b implies f of x1 is greater than f of x2. First derivative information about shape, part 1. For a function f which is differentiable on an interval from a to b, if f is increasing on a to b, then f prime of x is greater than 0 for all x in ab. If f is decreasing on AB, then f prime of x is less than 0 for all x in AB. If f of x is constant on AB, then f prime of x equals 0 for all x in AB. There's also the first derivative information about shape, part 2, which says for a function f which is differentiable on an interval from a to b, if f prime of x is greater than 0 for all x in AB, then f of x is increasing on AB. If f prime of x is less than 0 for all x in AB, then f of x is decreasing on AB. And if f prime of x equals 0 for all x in AB, then f of x is constant on AB. Continuity, a graph is called concave up if you think about pouring liquid on it and the water stays there in kind of a bowl-like. The following graph is concave up. A graph is called concave down if you think about pouring liquid on it and the water flows off, kind of like an umbrella. The following graph is concave down. Note, the book uses greater than or equal to and less than or equal to instead of greater than and less than in all of these statements. This is a mistake in the book. All of the statements about increasing, decreasing, and concavity should only involve greater than and less than. Graphs can have areas of being concave up and areas of being concave down. Lines have no concavity. Concavity does not imply anything about whether a graph is increasing or decreasing. The second derivative information about the shape. If f of x is concave up on AB, then the second derivative of f of x is greater than 0 for all x in AB. And if f of x is concave down on AB, then the second derivative of f is less than 0 for all x in AB. The converse of both are true. In other words, if f double prime of x is greater than 0 for all x in AB, then f of x is concave up on AB. And if f double prime of x is less than 0 for all x in AB, then f of x is concave down on AB. Inflection point, a point on the graph of a function f of a at which a change of concavity occurs is called an inflection point. To find possible values of the inflection point, f of double prime of a equals 0 or f double prime of a is undefined. So let's look at an example. Looking at this graph determines the intervals on which it is increasing, decreasing, concave up, or concave down. So the solution to this, the graph is going up from negative infinity to about -3. So here the graph's going up. And from about 2 to positive infinity. So the graph is increasing, so f is increasing. On the interval from -infinity to -3, and union the interval from 2 to infinity. The graph is going down from about -3 to about 2. So the function is decreasing on -3 to 2. The graph looks like an umbrella from negative infinity so from negative infinity until about 0, the graph looks like an umbrella. So it is concave down. Concave down from negative infinity to about 0. And it looks like a bowl from 0 to infinity. So F is concave up from 0 to infinity. Looking at the graph, you can get an approximate answer, but calculus can give exact answers. So example number 2, find the domains of the following functions and where the functions are increasing, decreasing, concave up, and concave down. So our first function is f of x is equal to x cubed minus 12x minus 5. So first, let's go with the domain. Since this function is in fact a polynomial, the domain is all real numbers. To find where it's increasing, decreasing, and concavity, find the first and second derivatives. So f prime of x is equal to 3x squared minus 12, and f double prime of x is equal to 6x. Now set both of these equal to 0. So, and then since you want to compare the derivatives to 0. So f prime of x is equal to 3x minus 12 equals 0. So 3x squared minus 12 equals 0. 3 times x minus 2 times x plus 2, when you factor it, equals 0. So x is equal to plus or minus 2. The second derivative is 6x equal to 0. So x is equal to 0. Now you want to look at the signs of both the derivatives on the different intervals. So here's a number line. This is for f prime, put negative 2 and 2 on the graph. For below negative 2, when I plug that a number less than negative 2 into my derivative, like say negative 3, I would get a positive number. If I put a number between negative 2 and 2, such as 0, into my derivative, I would get a negative. And if I put a number greater than 2 into my interval, I would get a positive. So f is increasing from negative infinity to negative 2, union 2 to infinity. And is decreasing from negative 2 to 2. Draw a number line for f double prime. Put 0 on there. This is for f double prime. If you take a number less than 0 into f double prime, you will get a negative number. If you put a number greater than 0 into f double prime on the number line, you get a positive. So f is concave down on the interval from negative infinity to 0, and concave up from 0 to infinity. The graph confirms this. Another example is f of x is equal to 5 minus x to the 1/2. Now the solution to this, the domain, since this function involves square roots, the domain is 0 to infinity, since you cannot take the square root of a negative number. To find where it's increasing, decreasing, and concavity, find the first and second derivatives. F prime of x would be negative 1/2 x to the negative 1/2, and f double prime of x would be 1/4 x to the negative 3/2. Now set both equal to 0 since you want to compare the derivatives to 0. Since neither derivative can equal 0, you want to look at the signs of both derivatives over the domain. So f prime of x equals negative 1/2 x to the negative 1/2 is less than 0 on the interval from 0 to infinity. So f is decreasing on 0 to infinity. F double prime equals to 1/4 x to the negative 3/2 is greater than 0 on the interval from 0 to infinity. So f is increasing on the interval from 0 to infinity. The graph confirms this. The next example is f of x is equal to 2e to the x minus x e to the x. The domain of this, since this function involves an exponential, the domain is all real numbers. To find where it's increasing, decreasing, and concavity, first find the first and second derivatives. F prime of x would be 2 times e to the x minus, using the product rule, the derivative first is 1 times the second e to the x minus x times the derivative of the second, which is e to the x. Factoring this, you'll get e to the x. I'm sorry, simplifying this, you get e to the x minus x e to the x. The second derivative is e to the x minus e to the x minus x e to the x, again using the product rule. So you get minus x e to the x. Now set both equal to 0 since you want to compare the derivatives to 0. F prime of x equals e to the x minus x e to the x equals 0. You want to factor that, pull out an e to the x, and you get 1 minus x equals 0, and x is equal to 1. F double prime of x is equal to minus x e to the x equal to 0, and that will be when x equals 0. Now look at the signs of both derivatives in the different intervals. Here's a number line for f prime. Put 1 on the number line. If you're less than 0 or less than 1, like such as 0, and you plug that in, you're going to get a positive number. If you're bigger than 1, such as 2, and you plug it in, you're going to get a negative number. So f is increasing on negative infinity to 1 and decreasing on 1 to infinity. For the second derivative, the number line will put 0 on the number line. If you take a number less than 0 and plug it into the second derivative, like -1, you will get a positive number. Put a number bigger than 0, like 1, into the second derivative, you'll get a negative number. So f is concave down. On the interval from -infinity. Sorry, concave down on the interval from 0 to infinity. And f is concave up on the interval from -infinity to 0. The graph confirms this.